Hi, welcome to online tutorial videos from jcbro. So in this video we will learn about encoders and their types and their applications. Furthermore, we also provide online training, help in technical assignments and do freelance projects based on embedded system, Matlab, Python, etc. So if you have any such requirement, then you can contact us through our website, that is www.jcbrolabs.org, or you can also mail us at info@jcbrolabs.org. So let's start about encoders. So when we talk about encoders, so first thing comes into our mind, like encoders are a device which encodes some physical quantity into the form of some electrical pulses or something like that. So similarly here encoders terms is used which encodes the motions in a form of electrical pulses. So if we talk from the definition point of view, then encoder can be thought of as a electromechanical devices that provides an electrical signal. So electromechanical device means there is an electrical component as well as a mechanical component involved in this encoder part. Okay, so basically it turns this mechanical motion in a form of electrical signals, and generally it is used in many industry where precise motion information is required. Okay, so here's a very simple example of a rotatory encoder. So, or you can think of a working of encoder. So there is a slotted disc which is connected to a spindle which is rotating through a motor or any other rotating device. So in this slotted disc there are some gaps are there, and then there is a light source which is generally could be like laser or could be LED, and then there is a detector, it could be a photo detector. So when there is a slot comes in front of this light, so it falls directly on a light encoder and it gives high. When there is no pulse on this light detector, then it gives 0. So this is how a simple working, and the same concept of working can be incorporated in a different forms. Like in this case, so you will find there are several cases in which we got two different outputs. So there are two laser sources or two lights. I should say the light source is one only, but there are two detectors which are placed a small distance apart. Right, so that when the pulse starts on this blue line earlier than that of the green line. So we use this kind of arrangement in order to further increase the accuracy of this pulse system, right? Now there are different types of encoder, like based on the types, like there could be rotatory encoder and linear encoder. Now both the rotatory and linear encoder could be of incremental encoder type or absolute encoder type, and then there are sensing technology, like there could be optical encoder, magnetic encoder, mechanical encoder, or inductive encoder, capacitive encoder, or the laser encoder. So in this case we will be dealing with the optical encoders only. So the principle is very easy for this optical encoder. Otherwise the entire working is same for different kind of encoders as well. So this is the internal diagram. As we said, there is a rotating wheel or rotating machines which have a spindle, and the slotted disc is connected to it, right? And there is a light source which will emit light from one side, and then there is a photo detector assembly which will be detecting the pulses coming from this light source, and there is a electronic circuitry which is finally generating the corresponding output, because this photodiode can give like whether there is a light or not, and with the help of op-amps or some other circuitry we create this information from this photodiode in a form of electrical pulses, right? Now this is again a different kind of rotatory encoder where the absolute position has been encoded in a form of a binary digits or in a form of binary code. So here we have, let's say 1 2 3 4 5. So there right now in this image there are 5 light sources and 5 detector as well, but there could be 3 light sources or 2 light sources. So if there are 5 light sources, that means maximum number resolution could be 2 to the power 5, or 2 to the power 5 different states can be formed, right? Now the linear encoders are this, like those were the example of the rotatory encoder. These are the example of the linear encoders, and these are the example for the rotatory encoder. Now about this absolute encoder, there is a simple example. There is another one where we are only using 2 bits to represent a state. So when there is a white, it will 1, when there is a black, it is 0. So we can encode this entire motion in a form of ones and zeros only. And there is an example where we have absolute encoder with 3 light sources. So they are we can say the binary encoding information is in 3 bits. So what is happening here, this if there are 3, that means the entire thing can be represented, this entire 360 degree of revolution is encoded in a form of a 3 bits. So 3 bits can be represented as 8 different states, like 0 0 to 0 to 7. So this entire 360 degree rotation can be divided into 8 parts. So one segment corresponds to the 45 degree. So this 45 degree comes after dividing this 360 degree by 8. So that means this one block where the code is not changing is for 45 degree of rotation. So by this we can find the how much absolute degree this wheel has been rotated. And these are the normal incremental encoders. So in this incremental encoders, there are simple light pulses, and then we count those pulses, and based on those pulses we just get like how many pulses have been total, how many pulses have been counted. So that is why it is an incremental encoder. So let's say if there is in one complete revolution there are 16 slots are there. So in one complete revolution we will get 16 pulse count. So if our pulse counting circuit represents 16 pulse, that will indicate okay, one complete revolution has been taken by the wheel. And these are the absolute encoder, as I discussed in the earlier way. Like based on this binary code, we can find like how much angle we are rotating. Okay, these are the square pulses which comes from the encoders, like an incremental encoder, as we showed in our earlier slide. Like there comes the 2 pulses, and based on these 2 pulses we can finally count like how many pulses have been passed. Now there is another term which represent like pulse per revolution. This is generally for incremental encoders. So as its name suggests, it generates like how many pulses we are getting in a complete revolution cycle. Okay, so let's say if the PPR count is 4, so pulse per revolution is 4, right? So in complete one revolution of one complete revolution of a rotating device, we will get only 4 pulses. And if we simply divide 360 by 4, that means one revolution or one pulse count represents about the 90 degree of the revolution from its current position. Similarly, if we increase this pulse per revolution count, then it already increase, we get further increase in the resolution, so that now one pulse can be represented, can represent or will represent this 22.5 degree. Similarly, there are count per pulse. So this count per pulse means how many pulses we are getting or counting in per revolution, right? So count could be like high or low, and can go by this waveform accordingly. Now this is the general structure of a DC motor which is fitted with the encoder, and we will see it in a live demo, like how the pulses are generated on a CRO. So we have a DC motor in which some Hall sensor based magnetic encoder is connected, and then we will see how the pulses are being generated there. Okay, so you have seen in your video like how the pulses were generated on the CRO. So I hope the video is informative for you to understand the basic working principles of the encoder and how to use them. So in our next upcoming video, we will be interfacing this encoder with the help of a microcontroller in order to absolute rotate, and we will be writing a code to rotate the DC motor by any specific angle or by any specific amount. So that's it for this video. Thank you.
Okay, so friend, here is our DC motor, and it is encoder connected, DC motor connected with encoder, and this is the encoder which is connected at the back side of this DC motor. So this is a geared DC motor, and this is the gearbox, and we have provided power supply to this DC motor. So we are providing a direct power supply 12 volt and 5 volt, 12 volt to this DC motor, and here are some of the connections to the encoder. So first two pin are the power supply to DC motor, then power supply to the encoder, and then these last two pins, yellow and white color, these are the encoder output. Okay, so we have connected this one pin of this encoder output to the DSO, and we will be showing like how this incremental encoder waveform comes into a real time. So let's start the motor. Okay, so here you see a very clear cut square pulses which comes from the encoder of this DC motor. So it is running at a particular speed, and now if we count like number of pulses coming in 1 second, from that information we can compute like what is the RPM of this DC motor, and now after counting the number of pulses we can also measure how much distance this particular motor has covered in terms of centimeter or meters. Okay, so this is all about the working of encoders, and this was the example of this incremental encoder. Okay.